So, for this, out of a total of R residents at a nursing home, the number of residents who have been infected by the flu increases as a rate proportional to the product of the number of residents who have had the flu and the number of residents who have not had the flu. If S denotes the number of residents who have had the flu at time T, write a differential equation that could be used to model this situation where K is a positive constant. I don't know why I put A right here on this. There's no part B to it, isn't there? I don't know why I put that A right there. Maybe I used to have the second part of this and I took it off. I can't remember. But this is not really asking you to solve a differential equation. It's asking you to write the differential equation, which we pretty much did some at the very beginning in that very first part of this unit. So it's just really like reading and interpreting what it's talking about. So it tells us here that it's important to know like what your variables mean. So S is the ones who have had the flu, number with flu, and T is our time, and we are supposed to write a differential equation where K is a constant value. So you're basically reading this and interpreting. It says out of a total of R residents, well, I should probably say capital R is the number of residents here. So out of a total of R residents at a nursing home, the number of residents who have been infected by the flu increases at a rate proportional to the product of the number of residents who have had the flu and the number of residents who have not had the flu. So if we kind of walk through this, we got number of residents who have been infected, number of residents who have been infected, what variable is that? That is S, but it says increases at a rate. So this, like, full thing right here is going to be ds dt. So it's the rate that the number of flu cases is increasing. Increases at a rate proportional to, that tells us that we do K times a value. And then it says the product. What's product tell us to do? Multiply. So we're going to multiply the two things that come after this, right? We got the number of residents who have had the flu. What is the number of residents who have had the flu? That is S, and it's a product, so we need to multiply the number of residents who have not had the flu. What's that going to be? Okay, R minus S right here, because R is our total number of residents, and you either, in this case, you have either had the flu or you have not had the flu. So we take our total number and we subtract the number who have had the flu, and that will be our differential equation there. If they wanted you to solve it, they would have to give you more information later on to fill things in here. And this kind of makes sense because like those two values, as S goes up, R minus S goes down, those two kind of like balance each other out here in that case. So that you will see probably on multiple choice section, you will see a couple questions like this where you're not really solving, it's just asking you to interpret and write that differential equation for those. All right, let's do another type of problem that we could have here. Whenever we did related rates, we did a lot of like water leaking out of tanks sort of problem, especially like there's a conical tank that is leaking. But in reality, if you just have like a hole in a tank, it does not leak at a constant rate. If you're pumping water out of a tank, it would be pumped out at a constant rate. But whenever you have like a hole in something, for example, let me give you a good example. Over the weekend, I went to Zaxby's, and I got some drinks, so like takeout. I was putting it in my car. Henry had been to the Lego store and bought some little Lego minifigures. He left his Lego minifigure that had a sword laying in the cup sitter on its back with its sword stuck up in the air right there in the cup sitter. So I go to put my drink in the cup sitter, and then it doesn't go in all the way, so I pull it back up. There's a Lego man stuck to the bottom with the sword pierced up through the bottom of the cup. So I had to leave the sword in the cup so it would like leak more slowly, and I ran back in, and Caitlin Bobbitt gave me a new cup to put it down in, and then I went on my way. But if I had taken the sword out, it would come out really fast at first, and then it would sort of slow down a little bit, because the weight of that liquid pushing down makes it come out faster at first, and as that weight of the liquid is less, it doesn't come out quite as fast at the end. So really, if you want to be really accurate, if you have a leak, you need a differential equation for that leak. So this is sort of what that's talking about here. So a tank with a volume of 30 cubic feet is leaking. The rate of change of the volume with respect to time of water leaking from a tank is proportional to the cube of the volume. Okay, so we're going to need to write a differential equation for this relationship. So we got volume here, we've got time, and it says the rate of change of the volume, what's that going to be? With respect to time, that's going to be dV dt, leaking from the tank, is proportional to, what did I put for that? Equals K times something, right? The cube of the volume. That would be V cubed right there. So that's a differential equation for this situation. Can't remember where I got this from, but I'm thinking that is actually like correct. Maybe. I don't think I made up that problem off the top of my head. So, so we could, measure this for my Lego sword experience over the weekend. So then they give us some information. At t equals 0, the tank is full. 30 minutes later, the tank has a volume of 25 cubic feet. Find how long it will take for the tank to have only 10 cubic feet of liquid left. So now we need to actually solve this. So we need to solve that differential equation first. You can't plug the numbers in before you solve the differential equation because you don't know dV dt, nor can you find what's going on there. So we got to separate variables. We've got dV dt equals K times V cubed. So we would multiply by dt, and that will give us dV equals KV cubed dt. What do I need to do now? Divide by that V cubed because it needs to be over here on this other side. Here. I could write it as dV over V cubed. You run a risk of accidentally doing a natural log right there. This one's not going to have a natural log on that left side, or either side, I guess. So how else could I write dV over V cubed? V to the negative third dV would be beautiful. And then we've got K dt over here. It feels like K is a variable, but it's just a constant. So we just treat it like it's a 2 or a 7 or something there. So now we have our variables separated. Everybody good here? All right, what do we do next? Integrate. So we're going to integrate. So I would increase my exponent by 1, which will give me a negative 2 right there, and multiply out front by, not multiply, divide out front by that negative 2, which will give me a negative 1/2. And then on the other side, what do I get when I integrate K? No. 0 would be the derivative, KT, because we're integrating with respect to t. So K is just like a number like 2. If it was 2, we'd have 2T. All right, so this is going to be KT. And what else do I need? Plus C. Can't forget that plus C or you won't be able to do the rest of the problem for that. Are we okay here? Very good. All right, so do I want to plug stuff in, or I think I'd rather solve for V first, maybe. I think it might be easier if I solve for V first. So this is negative 1 over 2V squared equals KT plus C. So what would I need to do first here? V. Let's solve for V. Okay. We multiply by 2V squared. Then we got negative 1 equals KT plus C 2V squared. All right, then what do you think? Okay, divide KT plus C. So now, I'll write it back up here. I got negative 1 over KT plus C equals 2V squared. Divide by 2. I'm going to multiply by 1/2 so that I don't have to like do a complex fraction right there. When you do this, make sure this is in parentheses. So you got negative 1 over 2 times KT plus C equals V squared. Yeah, and then we would square root, which will give us a plus or minus right there. So we got like our V equals plus or minus the square root of negative 1 over 2 times KT plus C. Now, whenever you're solving a differential equation, when you get that plus or minus, you need to choose a plus or minus in this case. V, what does it stand for? It stands for volume. Is volume going to be negative? It is not, right? So in this case, because everything we should be dealing with is going to be positive, we want to choose the positive here, so we could just say that the volume equals negative 1 over 2 times KT plus C. In a different scenario, we would probably need to like look at our initial conditions. Here, our initial conditions are definitely positive here because we will only be looking at positive values. All right, so we need to find K and we need to find C. So it tells us at T equals 0, the tank is full, right? And it told us that the tank held 30 cubic feet. So I've got the point 030 that I could plug in here. So that would be 30 equals the square root of negative 1 over 2 times K times 0 plus C. So 30 will equal the square root of negative 1 over 2C. What do I need to do now? Square both sides. So that will give me 900 equals negative 1 over 2C. What now? Not 1/2. C's in the bottom. We can't solve for C while it's in the bottom. So let's multiply by 2C on both sides. And so that'll give me 1800. C equals negative 1. And I'm going to divide by 1800. It's an ugly C. but we found it. So negative 1 over 1800 is our C. So if I go back up here, V equals square root of negative 1 over 2 times KT minus 1 over 1800. Yep. Okay, questions here? Alright, I'm feeling nervous. This feels bad. But I don't think we've messed up yet. I hope not. Alright, what should we do next? Because we still can't solve this because we don't have a K right here. We got two variables. So what should we do next? Okay, we got 30 minutes and 25 cubic feet, right? So 30 minutes and 25 cubic feet is going to go in. So we got 25 equals square root of negative 1 over 2 times K times 30 minus 1 over 1800. This is not pretty, but we can do it. So we will, I'm going to have to get rid of that. I'm going to do two steps at once. I'm going to simplify the bottom, but I'm also going to go ahead and square both sides because I got to get rid of that square root. So 25 squared, is that 625? Or am I wrong on that? Or it might be 12. 25 squared is 625. Alright, so we got 625 equals negative 1 over, here I'm going to just go ahead and distribute this 2. So that's going to give me 60K minus, that'll be 2 over 1800, which will reduce to 1 over 900. And this would be calculator active, but I just prefer to deal with the fractions for right now because they haven't gotten too bad instead of decimals. But you could do decimals, just don't simplify. All right, how do I solve this? Multiply by this bottom stuff because you can't solve for it while it's in the bottom. So that'll look like this. We'll get 625 times 60K minus 1 over 900 equals negative 1. All right, we're getting close. It's getting better. Distribute. So 625 times 60 is 37,500 K minus, I'm just going to write it as 625 over 900 right now, equals negative 1. What do I need to do now? Add 625 over 900. Which will be 37,500 K equals 275, negative 275 over 900. You can go decimals here if you'd rather, in that case. Last step. Divide by 37. At this point, I'm definitely going to go ahead and just go decimals for this. So I've got negative 275 over 900 divided by 37,500. And, oh gosh, it even gives you it gives me scientific notation when I type that in. So I got negative 8.14814 to the negative 6. So that's moves that decimal place 6 places to the left. It's a really small number. It feels wrong, but I hope it's not. It is fun. The tank is probably empty by the time we figure out what is happening here. Yeah, because we're really still not done. Although I think I'm about to jump to Desmos after this. This part all has to be done by hand, but now we do have the equation. We got V equals the square root of negative 1 over, let's see, well, where was my equation? 2 times, I'm just going to put K right here, but we know what K is. When I type it into Desmos, I'm going to use that full decimal for K. So it was KT minus 1 over 1800. So they're obviously going to have to give you this. First of all, they're probably not going to give you one quite this intensive, or if they do, it'll be broken into steps. So like it'll be solve the differential equation, then it'll give you conditions. So like it'll be free response. You'll get like points along the way. But obviously this would have to be calculator active if this is the case. So if we go over here to Desmos and we graph this equation that we have here. So I'm going to do V of T equals square root of negative 1 over 2 times, and then the decimal I've got here is, oh gosh, it's negative 8.14815 times 10 to the negative 16. If I had done this whole thing in Desmos, I could have copied and pasted. T minus 1 over 1800. Let's look at this all together to make sure it looks okay. I think this looks good. That K, this is that K value I got in my calculator there. So that gives me this graph that looks like a straight line. So we want to know when y equals 10 here, and we know that red line should be dropping, right? We're gonna have to abandon this problem, aren't we? Because something's not right. Let's change the x-axis here.
I'm pretending it's right.
Oh yeah, something's very wrong. I was feeling a little nervous. As we're gonna have to abandon it. We don't have time to fix it. I don't know where we went wrong. I'm pretty sure it's somewhere along here with this K being that. Oh, I know. I typed it in as a 16 instead of a 6. Maybe it's not as bad as it looked. Oh, look, there now our graph. Okay, all right. I think I just had that typed in as 16 instead of 6. This looks better, right? Because we can actually see it decreasing.
Yeah.
So if I zoom in, zoom will work, I think. And if I zoom out.
Why do we have E on the board and then Karen on the?
That was the calculator notation.
Okay.
The calculator is not actually like E. I shouldn't have written it like that.
Okay.
This is scientific notation right here. I should have written it this way, times 10 to the negative 6 power. The calculator uses a capital E. I shouldn't have written that lowercase e for sure because that is a mathematical symbol.
Like E.
Yeah.
Like
No, I understand why I should not have done that. That was bad notation. Okay. I think this seems reasonable as well, right? Because 545 minutes is a much more reasonable answer. So T equals 545 point. No. I mean, probably somewhere. I feel pretty confident about this, though. This feels good. Well, I don't know. I mean, we still got this done quicker than the tank would be down to that point, right? Like, a lot faster than that. Faster than waiting for the tank to drain.
I wouldn't be able to get done on the FRQ.
Yeah. Now, this is what they'll probably do if you see something like this. You might see it, but they probably won't ask you to solve it all the way on one like this because it is, they might give it to you where they've already plugged some of the numbers in, so it's easier. They may only ask you to write the differential equation. On the actual AP exam, you're unlikely to have to go all the way to the end on that because it's pretty extensive for that. So I got one more Newton's Law of Cooling problem I'd like for us to do. I don't know if we'll fit it in. Also, you guys eating some Hot Pockets here? Like, I don't know if I grew up in the microwave era. I don't know if it was just my family, but I'm pretty sure like everybody ate a lot more microwave food whenever I was a kid. So, I mean, we had a freezer full of Hot Pockets at some points. If you haven't had one, you know, it's like, it's got like bread on the outside and it's full of stuff. I think this is funny, so I'm going to show you even though we don't have time. Yes. Let's see. Let me cut the volume off on it. I'm sharing that with you because I figured that you guys have not eaten as many Hot Pockets as I have in my day, but that is accurate. They're either like still frozen in the middle, or you got them way too hot and they are going to destroy your mouth. So on Monday, I'm going to bring some pizza rolls, not Hot Pockets, because I'm not going to get Hot Pockets for the whole class. You might not even like them, but I'm going to bring you some pizza rolls because they're kind of like tiny Hot Pockets, and we will do a lab with our pizza rolls here, because we could use Newton's Law of Cooling to get our Hot Pocket or our pizza rolls to the optimal eating temperature, right? So that we do not burn our mouth or have a frozen Hot Pocket. Newton's Law of Cooling, we said it's kind of given to you here. They're probably not going to call it Newton's Law of Cooling if you see it in a problem. It's going to say something like the rate of change of the Hot Pocket's temperature with respect to time is proportional to the difference between the Hot Pocket's temperature in degrees and the room temperature of 73 degrees. Write a differential equation that describes this here. So, like we did the other day, it's d capital T over d little t equals your temperature is proportional to, your rate of change of the temperature is proportional to the difference between your temperature and your ambient temperature, which in this case is 73. Right? So in this part, they're just asking you to write that differential equation. Then they give you all the information that you need to know. Because I don't have a lot of room because I just have room right here, I'm going to go ahead and solve my differential equation right here, but it's not really what they're asking you for on that part. So if I multiply by dt, I got d capital T equals k times t minus 73 dt. What do I need to do? Divide by t minus 73. So I've got d capital T over t minus 73 equals k dt. I'm going to integrate both sides. This is technically a UDU, but because the derivative of t is just dt, it just ends up being natural log of the absolute value of t minus 73 equals kt plus c. And then we want to go ahead, it'll be easier if we go ahead and solve this for t. What should we do? E to the power, we got t minus 73 equals, what happens to that c? Comes to the front as a big C, CE to the KT, and then we'll move that 73 over. So we got t equals CE to the KT plus 73. So whenever we do our lab on Monday, it says 20 seconds after being removed from the microwave. The temperature of the hot pocket is 205, and then 1 minute it's 187. We're going to have to do this as well, because when you take something out of the microwave and you measure its temperature, it takes a little bit for the thermometer to read the temperature, right? It keeps going up until you get to a certain point. But it's going to be hard to solve this problem if we don't have t equals 0, right? So what we're going to do is we're going to pretend like this is t equals 0, which would mean 1 minute, where's 1 minute, would actually be t equals 40 seconds. And just remember, we need to add 20 seconds to our answer at the end. So add 20 seconds at the end of this problem. We'll make ourselves a note right there so we try not to forget it. So we would start off with our capital T. We got 205 equals CE to the K times 0 plus 73. E to the 0 is just 1, so 205 equals C plus 73. And then we'd subtract that 73 to get 132. I'm sorry, 172, right? No, 132 was right. 132, right there. So now we've got capital T equals 132 e to the KT plus 73. Now we'll plug in our other piece of information that we've got. So we got 187 equals 132 e to the K times 40. We'll run out of time again, just like the end of class yesterday. And so we would need to finish solving this. We'll get our equation, and then we can see when it would hit the optimal eating temperature of 150. We're out of time, so we're not going to get to know what to do, but we'll do another problem like this because we're going to do it as our very short little lab that we'll do.